So in the last class, we have discussed how we found the shortest distance between a line and the XY line. So we just converted the XY line into a point using our auxiliary method, and then we drew a perpendicular line from that point to the projected line. Here, this is the XY line. When a line is seen perpendicular to it, like from this side, it will be visible. It will be projecting as a single point. So this is point O. So when we are projecting a point, XY line as a point, we should also project the A dash B dash. So we projected A dash B dash also, and we got A1 B1, which is called as auxiliary front view. Now we join this point perpendicular to the line, and then see, this is the line perpendicular. Now we measure this OM, and we say this is the shortest distance between the line AB to XY. Now let us see the next part. So this is just the description of that. How do we get that? So that you can refer it later on if you have any doubts. So how do we convert the line into a point? So it is the point is simple. You have to see. You have to take a projection perpendicular to the line. Then you will get the you can convert the line as a point. So for that, what you need to do is initially you should know where is the true length, which one is the true length of the line. So for that, what you have to do, when you already have two projections, front view and top view, you try to get the true length. You can do it either in using the top view or using the front view. I mean, using the top view or the front view. Any way you can do. Here we started from the front view. We took the projections. We took the auxiliary plane x1, y1 first, and then we drew the perpendicular lines from A dash, B dash, and we extended those lines. So how far do we extend them? We extend the these dimensions d1. From A dash we extend d1, since A is at a distance of d1 from xy line, and from B dash we extend d2, since B is at a distance of d2 from xy line. So then we join these 2 points to get the true length of AB. Now when you see this line from this angle, when you see this line from this angle, wait, like this. Yes. So when you see this whole line from this angle, you will observe them as a point. These ends A1 and B1 both will coincide. So then you will get a point. So here you took an auxiliary front view. So what will the dimensions of this be? A1 and B1. Now when you take another auxiliary plane, when you take another auxiliary plane, then you get the other view. So here what happens is that this is the auxiliary top view. Just a correction, this is auxiliary top view. So this is A1 and B1. Now when you take another auxiliary plane x2 y2, and when you take these projections, now you get auxiliary front view again. So you'll not be getting continuously front views as you keep on taking auxiliary planes and projections. So once if you get an auxiliary front view, again if you take a projection using an auxiliary plane, you get an auxiliary top view. So this repeats one after the other. So now this is the auxiliary top view. So it is A1, B1. And now when you project it again using another auxiliary plane, you get auxiliary front view. So now this is labeled as A1 dash, B1 dash. So this is the point. This is the point form of a line. So that is how a line is projected as a point. So this is the conclusion. Point view must always follow true length view. So now what we do is we try to get the shortest distance between a line and a point. Between a line and a point. So again we'll do the same thing. If you get the true length of the line, then you can measure the perpendicular distance from the point to true length. So that is one method. Or you can convert the whole line as a point. So this is already a point. P1 is a P is a point P. So here is the top view, here is the front view. So when you use auxiliary methods to convert to get different projections of a point, what do you get? A point will be we will be getting a point as a point only. So that doesn't change. So our aim will be to convert this whole line AB into a point. Then so that we can measure distance between our point P and these projected points AB, and then we can measure them. So that is how we get the shortest distance. So this is the shortest distance. So let us see how do we proceed now. So now there are projections A1, A dash, B dash, and AB. So this is the top view, this is the front view. Now we start taking the auxiliary planes. So initially you start with one auxiliary plane x1, y1. So this is the x1, y1. Now you project from A dash and B dash, and you take D1 here, D1, D1, and D2 and D2, and now you join these 2 points to get the true length of AB. Now you got the true length A1, B1 is the true length. So now what will this be? Since you have projected from front view, this will be our auxiliary top view. A dash A1, B1 is the auxiliary top view. Now, now simultaneously, what should we do? We should also project the point P dash. So now in the same fashion as we developed A dash, we also draw a perpendicular from P dash to auxiliary plane, and then we extend it. How far do we extend it? How how far is the point P from XY line? That is D4. We extend that much. Now we got a auxiliary top view here, P1. Now it is labeled as P1. Now see this is a simple way. So you can directly draw a perpendicular here, and you can measure it. Directly draw a perpendicular here, and or what you can do is you can take another auxiliary plane x2 y2, and then so this auxiliary plane x2 y2 is perpendicular to this a1 b1. Okay, so now what happens is, now when you take projections of a1 b1 using this auxiliary plane, you get a point here, a1 dash b1 dash. So this is our auxiliary front view, a1 dash b1 dash. Now you should also project this p1 using this auxiliary plane x1 x2 y2, and you get the point here p1 dash. P1 dash. So now it's simple. Now you measure distance between A1 dash, B1 dash, and P1 dash. So that gives you the true distance of a point from the line A, B. So any doubts in this?
Yes, I have a doubt. How to calculate the shortest distance? Can you calculate it by the geometry?
Sorry, I was not able to hear. Any doubts?
Am I audible? Hello, am I audible?
I'm not able to hear you. There is a lot of noise. Can you put it in the comments if you have any doubt?
Yeah, okay.
Okay, I think there are no doubts. Let us proceed. Okay, so right. Now, so we have seen how to get a shortest distance between a line and a point. So these are the construction, how to do the constructions and how to obtain the shortest distance. You can refer them after this PPT is given to you. So if you have any further doubts. There is one more thing. Maybe I did not mention. So for first auxiliary projection, you took the dimension from here. So you took a D1, D2, and D4. and you obtained A1, B1, and P1. Now, what are the dimensions you needed for getting another auxiliary projection? So here, what you have to do is the the projections which are used to get this auxiliary projection are the dimensions we need. That means, so these are the projections. These are the projections using which we developed these. So now what we have to do is we have to measure the dimensions of these projections from the auxiliary plane. So now here we are taking D3 and this is D5. We are taking this D3, D5 to obtain these points A1 dash, B1 dash. See, this is D3 and this is D5 to obtain these respective points, and then we take the shortest distance. So you have to proceed in this fashion. So if you have to take, if you want another auxiliary projection, say you are taking somewhere here another auxiliary projection. So then what you have to do is you have to measure these this A1, B1 from this auxiliary plane, and then use those dimensions to get another auxiliary projections. So that is how you have to do. So now let us see planes. How are oblique planes uh, projected as an projected to get a line like this? So what is the purpose to do this? We'll see in the following slides. What is the purpose? So let us see first how are the planes converted into a line using an auxiliary plane. So now using the dimensions and orientations given, you will be getting these projections A, B, C, and A dash, B dash, C dash. So this is the top view and this is the front view of the oblique plane ABC. Now, how do you convert this into a line like this? So now everyone now understands why I am saying that this plane is converted into a line. How a plane is converted into a line. I hope everyone is comfortable with that. It is similar to how a line AB, as we have seen here, a line AB is converted into a point. In similar fashion, we are converting a plane into a straight line. It's just that we are reducing one of the dimension of it. That's all. Now what you do is you draw a line which is perpendicular, I mean, which is parallel to XY line. So this is AD, which is parallel to XY. So why do you do that? So we already know that when a line is parallel to XY line in any of the projection, then its true length will be shown in the other projection. What do you mean by that? When a line is parallel to HP, if a line is parallel to horizontal HP and is inclined to VP, then what will happen? You'll get true true length of the line in one of the projections. In what projection you get? If a line is parallel to HP, how does the projection look like? Uh, in front view, it will be a straight line, and in top view, you will get the true length. Similarly, when a line is parallel to VP and is inclined to HP, what do you get? You get the true length in the front view and a parallel to XY line in top view. So in the same fashion, we are doing this. So we take a line which is parallel to XY. So this AD, we chose AD, which is parallel to XY. Now this D point is obtained in front view also, D dash. Now what you do is you join this and you extend it further, A dash, D dash. Now if you why are we doing this? Because A dash, D dash is the true line, true length. So now when you see this plane ABC in this direction, now when you see this plane in this direction, you will get the projection of this whole plane as a line. So that is the reason we are doing this. So now what you do is you take an auxiliary plane perpendicular to this line A dash D dash. So this is that line A dash D dash, and you chose a plane x1 y1 perpendicular to this. Now you just project the A dash B dash C dash on and get the straight line. So everyone knows how is this projection. Then you take the dimension of A, B, C from here, D1, D2, D3, and from the auxiliary plane you have to measure that D1, D2, D3, and you have to just join them. So now what happens is A dash D dash will coincide to give a point. Everyone understands why this is a point. So this is a straight line and you are seeing perpendicular to it. So it gives a point. So that point is both A1 and and D1 both. So this is how a plane is converted into a straight line. So we'll go to the next one. So right now we have now this is our objective. So we have to find the shortest distance from the any point P and a oblique plane. So that is the whole purpose why we are converting a plane into a straight line. So that is the whole purpose. So now this using the same construction methods, what we do is we convert this plane ABC into a straight line ABC. So this is the plane, and similarly we project this point P dash. We project this point P onto the auxiliary plane, and we get the auxiliary projections. So this whole thing here is the auxiliary projections of a plane ABC and the point P. So now what we do is the shortest distance between a line will be a perpendicular distance. So we draw a perpendicular line and we measure that and we say that this is the shortest distance between the point and the plane. So I hope everyone understood this. Am I clear? Uh, if there are any more doubts, you can raise your hand or you can speak up. Okay, I see a thumbs up. Okay,
Yeah, Devansh,
great.
we can go ahead.
Okay, let's go. Let's proceed then. Yeah, so what is this? This true shape and size of the oblique plane. So yeah, so we have seen, depending on the orientation of ABC, we just obtain these projections, top view and front view, and then we have converted this into a straight line. Fair enough. We have converted into a straight line. Done. Now, what if we wanted to know the true shape of it? And why do we need that? Why do we need true shape of this? That you will see in furthermore lectures. What is the advantages of getting a true shape? Okay. So now how do we get the true shape of it? True shape of the plane. So when you see the plane exactly perpendicular to the plane, then you will see the true shape. So everyone understands? Now see, everyone are watching your laptop screens right now. So when do you see the true size of the laptop screen? When you are seeing exactly perpendicular to the screen. If you see parallel to the screen, what will happen? You will see the whole screen as a straight line. You will not able to see anything, right? When you want a really nice view of your laptop screens, what do? You see it in perpendicular direction. So in the same way here also, we have to see this plane ABC in perpendicular direction. So how do we do that? When we obtain this line, when we have already converted this ABC into a straight line ABC, I mean A1 B1 C1. Now when you see this plane perpendicularly, so that is from this direction. When you see this from this direction, you get the true shape of the plane. So yeah, you have to see this in this direction. Okay. So when you are observing from this direction, what does this mean? So this is the auxiliary plane you need, x2, y2. So now you have to get the projections of A1, B1, C1 on this auxiliary plane so that you get the true shape of the oblique plane. So now what are the dimensions you need to use to project this? Now to project this, you have already used these dimensions D1, D2, D3 here. So these are D1, D2, D3. You used these dimensions to get the straight line form of the plane. Now, if you are projecting again, I said I already mentioned this point. So now what you do? You go back one step. So this is the from here you are projecting. So you go back one step. So this is one more behind one step, previous step. So these are the dimensions. So this is the XY line for this projection. This is the XY line. So now from this X1, Y1, you have to measure these points A dash, B dash, and C dash. How far are these 3 points from our X1, Y1? Using these dimensions D4, D5, D6, you have to mark these points A1 dash, B1 dash, C1 dash, respectively. So the construction is the same. You draw a perpendicular and you extend it, and you measure if for getting from B1, so you take this distance D4 and you take this distance D4 and you mark the point B1 dash. Similarly, all everything A1 dash, B1 dash, C1 dash, and now you join these points to get the true shape of the oblique plane. So any doubts in this? How to get the true shape of the plane? You'll understand this in further topics when we discuss. Why is this important to learn? I think there are no doubts. Uh, okay, then let us proceed. So these are the just construction points you can refer if you even if you are stuck any time. So yeah. So this is another concept. What is the angle between two intersecting planes? So these are two planes A, B, C, and A, D, C. So here it is color coded also. One plane is blue color, one plane is orange color. Okay. Okay. So let us see what an example for this. Uh, everyone are everyone have your own laptops. So laptops open right now, right? So is it always you do you keep the laptop screen always in one particular direction, one particular orientation with your keypad? I mean, is it always perpendicular or is it always 30 degrees or something? No, you just keep pushing it up and down. Everyone is understanding, what I'm talking? See, you just keep pushing this laptop screen up and down. So the orientation changes. So so you should find the angle between the screen and the keypad thing. So that is one of the examples for this. So these are two planes, ABC and ADC. You have to find the angle between those two. So in the laptops, it's very simple. You just go in the direction. I mean, you take a side view. You convert the screen and the keypad into straight lines. I mean, convert in the sense you will see in such a way that the screen is a straight line for you and the keypad is a straight line for you, and then you keep a protractor there and then you can measure the angle. This is also the same thing we are doing here. So this is the front view, this is the top view. Now what we need to do, we need to convert the both the planes into straight line forms. So we have to convert A dash, B dash, C dash into straight line. Here this is the straight line, and we have to convert A, D, C, A dash, D dash, C dash into another straight line, and then we have to measure the angle between them. So then we get the angle between the two planes. So this construction is the same. I've already spoken how to convert the plane into a straight line. Using the same construction methodology, we convert another plane also here into a straight line, and we measure this angle theta, and we give this is the angle between the two intersecting planes. I hope it's everyone understood how to calculate the angle between the intersecting planes. Any more doubts in this or previous slides? Yeah, Chandrika Agarwal. Yeah,
Chandrika, you
go
can.
ahead.
Yeah, this thing, that topmost figure we made. So is it something like we rotate the
I don't know. I'm not able
rotate
to
them?
hear properly. Just a minute. Let me just.
I'll put that in the chat then.
Chandrika, can you repeat your doubt?
And the topmost figure we made is that we rotated that such that both the planes become 180 to each other, or what did we do? I did not get
This
that.
one. This one.
Yeah.
So we are not making them normal. We are just converting the planes into a straight lines. So this A dash, B dash, C dash, we are converting it as it as a straight line. So since A dash, C dash is on the same line,
Yeah, I got it.
we are
Got it.
getting this point as A1, C1, and this is
Hmm.
B1. And similarly, when you project this D dash, you get it here D dash, D1.
Yeah, I got it. Got it.
So this is the angle we measure. They are not perpendicular. They might be perpendicular. That is just a coincidence. That's all. We are not making them perpendicular. We are just finding the angle between them. Yeah. So any more doubts? Okay then.
Yeah, Devang, we can
Yeah,
go
we'll
ahead.
proceed.
Yeah.
Yeah. So these are some of the points. You can just read them, or I'll read them out. So see, these are some of the points which I already spoke about. When one view of the line is parallel to a reference line, other view represents the true length. So this reference line is nothing but XY line. So using this A dash, this is nothing but AD, which we have constructed parallel to it, and then we obtained the true length, and then we got the straight line view of the plane. So that is what it is. A line will appear as a point when it is projected on a plane perpendicular to it. So this is what we have done. Shortest distance between given point and given line measured along perpendicular drawn from point to line. So that is what we are using to get the shortest distance. Lines perpendicular in space have projections perpendicular in any view which shows either or both of the lines in true lengths. So when the lines are perpendicular in any of the in any one particular view, you get the true lengths of those lines. So that is what it says. When a line is perpendicular to a plane, it is perpendicular to every line in that plane. So this is simple. It is self-explanatory point only, right? Yeah. The shortest distance between plane and point measured along perpendicular from point to plane. Perpendicular seen any edge view of plane. So what is this edge view? Edge view is nothing but when you see from one of the edge, this whole plane will be converted into a straight line. So then you draw a straight line from this point to that line, and then you measure it. That is what this point is. A plane figure seen as line when it is projected on plane perpendicular to it. So that is what we did. A plane which is perpendicular to projection showing true length of line is perpendicular to line. Sorry, come again. A plane which is perpendicular to projection showing true length of line is perpendicular to line. Yeah, so Yeah, this is also the same thing. When a plane is perpendicular and you take the projection will also be the perpendicularly only. So that is what it says. A plane which perpendicular to true length view of line is perpendicular to plane containing that line. Yeah, this is also the same thing, the same point. Projection of plane figure on plane parallel to it will show its true size and shape. So that is what we are doing to get the true size and shape. We are taking a plane parallel to it and seeing perpendicularly. Then we get the true shape, size and shape. Edge view of a plane is obtained by looking at the plane with the direction of viewing plane to the plane. So edge view is nothing but you imagine yourself to be at one of the edge and you see the plane. So you get a straight line, I mean line projection of a plane. So that is nothing but parallelly you are seeing. Angle of intersection of two planes can be seen on a plane perpendicular to both planes. So this is what we have talked about, laptop screen and laptop keypad. You go yourself towards one side and you see, and then you get the angle, intersection angle of two planes. So this is something like a motivation why we are uh, why we are taking the projections of a 3D plane into a 2D line or something like that. So using this, we get the true shapes. We can find the angle of inclinations, and we can draw the principal views and everything, all those things to get the true shape and orientations. So these are the different planes, types of planes. And this is nothing but one first thing is profile planes. Everyone knows what are profile planes. Our main horizontal plane and vertical plane are the profile planes. And then we have a planes perpendicular to HP and parallel to VP and perpendicular to VP and parallel to HP. This is the same thing like a straight line where we have seen a straight line one by one. This is also the same thing. Planes also the same thing. Perpendicular to one thing, parallel to one thing, and then it is perpendicular to one plane and inclined to another plane. And at the end we get it is inclined to both the planes. Those we'll see one by one. So now here ABCD is the plane which is perpendicular to HP and is at an angle phi to vertical plane. So if you remember, this is what is this plane? We called it as auxiliary. Is it an inclined plane or a vertical plane? Auxiliary inclined plane or a vertical plane? It is the auxiliary inclined. It is the auxiliary vertical plane. So we have already seen how to project this also. So this is the true shape of the plane. Say this is the true shape of the plane, and this is the line form of the plane. But since it is at an angle phi, what do you do is we tilt this line to get this at an angle phi. And then what we do is we draw construction lines from this, and we draw these construction lines from these points like this, and then we get these points A1 dash, B1 dash, and extending this we get D1 dash and C1 dash. So this is the true projections of the plane ABCD. Okay. So this is the plane which is perpendicular to HP and inclined to vertical plane, which this is the auxiliary vertical plane, which we have already seen. So this is another orientation of the plane ABCD, which is perpendicular to vertical plane and it is at an angle phi to horizontal plane. So in the same way, we'll do construction here. So this is the initially we have to draw the true shapes of it. A, B, C, D. Yeah, ABCD, and then it is a straight line in another projection. And now we draw the construction lines parallel to XY here also. And then this is the orientation of the plane at an angle phi. Now we draw the construction lines from vertical construction lines, and then we find the intersection points, and then we label them. So everyone understands how these are labeled, right? Right. I just show you for one of the things. Okay. So now you have drawn this construction line here, and you have drawn this construction line. So how do you label? How do you get this as A1 and this as B1? Why not this as A1 and this as B1? So here we are extending the line from BD, and this extension line from BD is meeting the another construction line from AB. So what is common among these four things? B, D, A, B. So B is common thing. So that's why this point is labeled as B1. B1 because we have already used B. That's why we are using B1. There is no complicated thing in this. So we just label it sequentially. That's all. So similarly, this is this is A1 because here the common thing is A in this line, and in this line this is A dash. So this becomes A1. So like that we label them. So everyone understands. No, this is the first step to get the to draw the true shapes and a straight line. And the second step is to orient this line at an angle phi, whatever angle is given. Now we have to draw the extension lines. That is third step, and then label all these things. So then we get the final projections of the plane ABCD. So these are just the construction points. The projection of an oblique plane. Okay, so this is the triangular plane which was chosen. Now this triangle is a straight line here when you see it parallel from one of the edge. Okay. So let us see first what are the angles. So this is an isosceles triangle. See, it is given that AB is parallel to HP. And inclined at 60 degrees to the VP. That means this line AB is inclined at 60 degrees to VP. So since this is the first projections we are drawing, we don't take any angles. We just treat it as this plane is parallel to HP. And so we got front view as a straight line. So now in the very next step, what we do is we start taking the angles. So there is this surface making an angle of 50 degrees. So what does this mean? So this is the line representation of the surface. So that is the reason why what we are doing is this 50 degrees angle we are inclining here. We are tilting this line A dash C dash by an angle 50 degrees to satisfy this line surface making an angle of 50 degrees. So everyone understands now why is this line making an angle 50 degrees satisfying this line, this point of surface making an angle of 50 degrees. It's same. You can imagine this as your laptop screen only. Your laptop screen is making an angle of 50 degrees with your keypad. What does that mean? If you say this is your laptop keypad, this is your laptop screen. So isn't that true that 50 degrees is that is satisfying? Now when you go to the other angle and see, it satisfies. So that is why we are inclining this line A dash C dash to make an angle 50 degrees, and we say that yes, the surface is making an angle of 50 degrees. So now what you do is same thing that we draw the construction lines here and here, and then we extend this point C dash. We extend it from here. It will meet this point, and we'll label this as C1. Okay. Now that this surface is making an angle of 50 degrees is satisfied, we go to the other point. What is the other point? This base AB is inclined at 60 degrees to the VP. That means this is the point A1, B1. This should be at an angle of 60 degrees to VP. So how do we do that? Now we have to tilt this so that A1, B1 will make 60 degrees with XY line. That satisfies this statement. Yes, so this is what we do. We just tilted it. You take this figure and we tilt it and we obtain this. So this is the first thing we have to draw, A1, B1, and then you have to measure these lines, A1, C1 and B1, C1. And you have to cut an arc and get C1. So you get these 3 points, A1, B1, C1. Now since you got A1, B1, C1, you draw these vertical construction lines from A1, B1, C1, and you draw these horizontal construction lines from here, A dash, B dash, C dash, and the intersections will be A1 dash, B1 dash, C1 dash. And this is A1, B1, C1. So this is our final projections of the oblique planes. So everyone understood this getting the projections, right? If you have any doubt, you can speak, or else we'll proceed. Okay, let us proceed.
Can you please explain
So
the
here,
rotation
what is this?
upper triangle ones?
Yeah.
Can you please explain the rotation of the upper triangle ones? I didn't understand it completely.
Okay. In this figure or this figure?
The next one is this one.
The middle one.
No, last one, the third one. A1
Last
dash,
one.
B1 dash, A1 dash.
Last one.
Yes.
Yeah. So here, see, when they say a particular angle, you have to know this line to make an angle 50 degrees with XY. And we said, yes, now the surface is making an angle of 50 degrees. Now there is another thing. This base AB is inclined at 60 degrees to the VP. So what does that mean? This is the base AB. So why am I choosing the top view for this? It's because this base AB is parallel to HP. So see, it is parallel to HP. So you can't see this angle 60 degrees in front view. In front view, it will just be a straight line. So that's why we are choosing the top view to show this 60 degrees. Yeah, you have to imagine. I already told you, you have to imagine to draw these figures. Why top view? Why front view? So that's why we chose this A1, B1. And we rotated this line A1, B1 such that this line makes an angle of 60 degrees with XY. So this is our first step. Drawing A1, B1 to get 60 degrees is our first step. Now what we do is, we have already got this point C1. Now it is said that this is an isosceles triangle. So A1, C1 and B1, C1 are same length. So you measure one of the lengths. From this point, cut an arc. From this point, cut another arc. Both will intersect at a point. So that point is C1. It is simple. For getting C1, you need not, there is no angle, there is nothing like that. So just draw this and then you cut an arc, that's all. Now you join these two, you get C1. Now, since you have got one of the views, so this is the top view of our plane ABC. Now, from top view points, this A1, B1, C1, you just draw the vertical construction lines. These are construction lines. Now, and from here, you have to draw the horizontal lines, because this A dash, B dash is at particular height from XY. This doesn't change because this is at an angle. So that is why we are taking a horizontal line from here. And we see where is that line intersecting these construction lines.
And wherever it intersects, we'll see what is that point. See, this is a B1. That's why this is B1 dash. This is A1. That's why this is A1 dash. And this line is we are getting from C1. That's why this point is C1 dash. Because this is point where C dash is there. So we take the intersection of these two projectors and we label it as C1 dash. Now it is simple. Just join these lines, and your front view is this is the front view. This is the top view. Okay.
I have one more question. Like the angle of A1 B1 with XY in the top view should be the apparent angle, right? Not the true angle, and they have given the true angle, right?
Sorry, can you come again?
The angle of A1 B1 with XY line XY should be the apparent angle, right? They are given the 60 degrees the true angle, right?
Yes, that is because this line AB is already parallel to HP. Understood? You are true. You whatever you said is true. But because AB, the line here, see this, there is a statement here. The base AB is parallel to HP. That is the reason this apparent angle is equal to true angle only.
Yes, got it. Thank you.
Yeah. When that is also varying, then there is a whatever you said is true. We can't just say this is our final projections. We have to change this again to get our final projections accordingly. Okay.
Hello.
So any more doubts?
Hello.
Yes, someone is speaking. Who's that?
Mane Pro.
I can't see you. Okay, go ahead. What's your doubt?
Can you mark a 50-degree angle in the third figure?
Yes, here it is there, 60 degrees.
50 degree, 50.
Yeah, that's what. So you can't show all angles at once. So here you have given 50 degrees already. So accordingly, what happened is this point C1, which is supposed to be here, change it to this point. This is the true shape of the plane. But because the surface is at an angle of 50 degrees with HP, what happens? This height of the triangle reduces now when you see it from the top view. See,
Okay.
this is the actual height of the triangle, A dash C dash. But when you project it onto the in top view, it is reduced. You understand it, right? This is the height. Say height is h.
Yeah,
H cos 50. This is not, this length is h cos 50. So taking this, we proceed further. We from here after this point, we don't need this anymore, because these are the true shapes and true heights, true sides of the triangle. We don't need this anymore. We take this and we proceed. So when you have these projections here and we have proceeded from this point, we can say that this is already having this 50 degrees thing in this.
Okay, I understand.
Yeah. Yes, Samiksha?
Yeah, hi. So I had a doubt here. Like when we
Yes.
have drawn A dash, B dash, and in the second figure, when we have taken the angle, then we have taken it like not from the point A dash, B dash, but it's kind of shifted towards the right a bit. So is there any particular reason, or is it like
No, shifted towards right means
if you
you
look at this point, the
you mean
point
here
line,
here it is a point. Now it has become a line. That is what your doubt?
no. See, in the first figure, we have this point A dash, B dash.
Yes.
And in the second figure, now, when
Yeah.
you have, sorry, not the No, no, not the third figure. The second one, the middle one.
Acha, below one. Okay.
No, no, upper one, A dash, B dash.
Okay. Okay. Huh.
Here, yeah. So there is a little difference between A dash, B dash and the point from where you have started the line.
Acha, acha. It's just the making the diagram is wrong. That's all. It starts from here only.
Okay, okay. Thank
Don't
you.
worry. Don't worry. You are right. It starts from here only, and
Yeah.
this 50 degrees is maintained, and it goes like this.
Okay.
Okay. Yeah. So any more doubts? Okay. So let's proceed.
Yeah, Revant, let me just
Good
come
morning,
in.
sir.
Morning. No, I've been there in the room. Only thing is, I think this is taking a lot more time than what I thought, this examples and doubts. My guess is that I think we have explained enough. We will share the slides. I think we'll make those corrections like what was pointed out just now. But I think let students also apply a little bit of their mind and you know, and when
Yes.
the lab actually happens, that also happens. That also will take care of it.
Yes.
So,
Yes.
so students, we will share these slides, including the remaining, I think the 2-3 more remaining slides. Number one, after corrections, please. Okay. And when the lab happens, anyway, we can handle some more doubts. Because there's half an hour left, I do need to make a couple of announcements. Maybe it will take 2-3 minutes. And also today's class, fortunately, today's class is easy because once you do this projection of points and lines and even planes, what Revant has been talking about, the next one, which is projection of solids, is actually very straightforward.
Yes, sir.
So my suggestion is that we just pause here for a 2 minutes. I'll make some announcements. It's like a commercial break, and then we will. I'll maybe spend another 20 minutes or so on the projection of solids. Okay.
Yes.
Again,
Yes.
last part, if there is a time, Revant, just be hang around for the examples part of it. Okay. So let me first share the, because these announcements came up just today morning only, so I thought let me do that. First of all, this is our schedule. I think all of you are aware of that. Let me zoom in. So we are somewhere sitting now at April 29. Sheet 3 projection of planar features we are still continuing, but hopefully I'll talk about projections of solids also. Okay, that is today's class. And the 5th May, the lab class will be about this these things, right? Now Institute has announced the return to campus for first year students, I think around 17th of May, okay, which is like another 2-3 weeks from now. So I slightly changed the schedule to take care of your return to campus. One more announcement that Institute has made is that once you return to campus, the examinations will be in physical mode, okay, which is midsum exams. And the midsum exam schedule, which was earlier shared with us, and maybe it's still on the net, but now we just got a announcement today morning saying that the midsum exams will be around 30th of May. After you return to campus, about 1 week, 2 weeks after that, it will be around that. The dates are not yet known exactly. So the summary, to summarize, what you should remember is all of you are supposed to return to campus around mid-May or 3rd week of May. And last week of May and first week of June, most likely you are going to have the midsum exams in physical mode. Okay. So if we hopefully maintain this schedule, which you see here, which is projections of solids, we kind of do it today. Then the sections of solids the week next Friday class, and 13 May. After that, we look at intersection surfaces also. If you do sheet 7 also, that is great as per schedule. Otherwise, what I'm doing is I'm keeping a backup 27th May, a catch-up class, just in case we have some issue about return to campus or physical mode, or your physical lab is not ready. We'll just keep a option for catch-up class. If it happens, good. Doesn't happen also, is okay. We can always manage that. And then anyway, your midsum exam will be there. What I'm looking at the possibility is that physical mode, you will have at least maybe, if not 1 or 2 physical mode labs, which is the isometric views of solids. The 3D CAD solid modeling anyway is on your laptops. So we will see how to manage that on your laptops. We will give you some software which you can download or use on the cloud, but all the instructions will come at that point of time. Okay. So right now, only these things. Let us not get into discussion mode here. Whatever I told you just now, in case those are missing in the class today, we'll put it in the announcement in your Moodle, and then you can follow from that. Okay. So it's just to give you a little heads up about what may happen in the next 1 month. So with this, I'll share this, and I'll go to the projections. I have a couple of things also I want to say before I use my slides. See, I mean, the amount of time that we are spending, and Revant is, thanks to Revant on this account, in explaining things, I have a feeling that most of you are not reading the ND Bhatt or any drawing book. Okay, in a lab, this is a lab class. It is not a theoretical class. In a lab class, you are supposed to read up the book and you are supposed to come prepared for your labs and do the labs, right? This 1 hour, 1.5 hour lecture class is only to just to kind of familiarize you with the whole thing, right? Initial classes were fine because you're still getting into the whole thing, your first year students. But by now you have to read it yourself, visualize it yourself, understand it yourself, and come to the lab class. We can't be using this much of explanations in these labs. Okay, so maybe I'll use today's own this projection of solids as an example. I'll give you a feeling of what it's all about. But you are expected to now read ND book yourself and do that. So all of you, I hope you already have the ND book. Okay. So let me still go into the today's class. So solids projection. So we will share 2 slides. I mean, one is what Revant was showing after corrections, and this one also I'll show. Okay, so let me start from class number 5, lecture class number 5, and we are now looking at projections of solids. And look at the picture on the right side. So by solids, I mean now 3D models bound by some surfaces. We'll define all those things. Okay. And when you project those onto planes, and of course orthographic planes or auxiliary planes, we'll look at that. And those projections are what you're talking about in this class. Okay. So first of all, why do we need it? Because all real life objects are 3D objects. Even so-called planar objects or sheet metal, what we call as mechanical engineering. For a chemical plant, you have this several, let us say, pipes and structures which are made up of sheet metal, which once you open it up, it is a flat sheet. But even a flat sheet, of course, has some thickness, finite thickness, right? So in general, most of the objects are 3D solids, and we are now wanting to look at how they will look in a different views. So typical problems that we want to solve through this exercise is one is not only projections of a solid, but also the orientation of a particular solid or its faces in space. Okay. And number 2, like we did distance between a point and a line, or a distance between 2 lines, which was the last part of the last class. Those things can also be determined through the projections method. Okay. Now, just a quick recap, rehash of what you already must be knowing as general knowledge. So when we say solid, in the current context of the graphics course, physical graphics or even a computer graphics, if you look at it, usually we talk about solids as polyhedra. By polyhedra means bounded by planes, okay, and planes are called as faces. Now you can say that it may not be plane. Some of the objects will have curved surfaces, in which case we call it as, instead of faces, we call it as surfaces. But we will not talk about it at this point of time immediately. And in this drawing course also, we will not talk about complex surfaces. We'll talk about only simple surfaces like either cylinders or spheres. Okay. But let's first talk about polyhedra, which is nothing but an object bound by flat faces, planes or flat faces. So you must have heard about this tetrahedron, cube, of course, you know, and things like that. And within polyhedra, a shape which has all the faces, same shape, same size, is called as a regular polyhedra. Okay. So what are the examples? A cube, for example, has 6 equal faces. A tetrahedron, okay, it has, let us say, 4 equal triangles, right? Some kind of pyramid, of course, triangular pyramid, you can also say. Octahedron, dodecahedron, isohedron, so 8, 12, 20 faces and things like that. So all these you have come across in life, and we're talking about shapes like that. And some examples of shapes like this. For example, if you look at the the polyhedron, which has a pyramidal shape or a prism kind of a shape, as you can see. The base, let us say, is parallel to, let us say, one of the orthographic planes, right? Then it is a kind of a shape which is easy to handle in projections. Or a pyramid also, where you're looking at a four triangles, but a base which is a square, and the base is parallel to one orthographic plane and perpendicular to another orthographic plane. So one of the shapes, one of the faces of the polyhedron being parallel or perpendicular to orthographic planes makes the projection a little more easier, and we will look at that first. So going further, what about shapes which do not have flat faces? And in computer graphics as well as physical graphics, we have a term called as solids of revolutions. What it means is that you get a shape by rotating a plane about an axis. So if you rotate a circle, for example, around its vertical axis, you get a sphere. Similarly, if you rotate a rectangle about its one of the sides, or even an offset side, you get on one side you will get a cylinder. If you offset the one side, you get a hollow cylinder, for example, right? So all these shapes are nothing but solids or revolutions. Why this term is important is that when you go into computer graphics at the very last class, the CAD, computer design class, these come up as operations in your computer graphics or CAD software. So you'll actually take a 2D shape, and then you're going to rotate it, and you're going to get a 3D shape out of that. Of course, in CAD, you can do many more advanced things, but we'll talk about that when we get there. But this is just a quick thing about the kind of shapes you're talking about. Now we'll talk about projections of these 3D shapes. Okay, so that depends partly on the orientation of the axis of the solid. By axis, of course, axis of a cylinder or a sphere or even a cube, you can define an axis of the cube, right? So depending on the orientation of the axis of the solid with the reference plane, you can talk about now different kinds of projections. One is a projection of solids in a simple position. So axis is perpendicular to horizontal plane, vertical plane, things like that. Ideally, if axis is parallel to both HP and BP, even better, very simple for us. Or one of the axis, let us say, is parallel to an orthographic plane, and sorry, axis is parallel to one of the orthographic plane, but inclined to another orthographic plane, like the ones we have seen in the previous classes, a plane or a line, for example. So that we can look at it. And of course, the most complicated case where the axes are inclined to both the reference planes, both the orthographic planes. So we'll look at these one by one slowly. So I don't want to talk too much because you will get bored. So I'll keep the picture on the screen for some time. Just look at it and look at a solid as nothing but comprising of points and lines and faces, right? We already have looked at projections of points and lines and faces. Just think about that. So actual solid is A, B, C, D, E, F. So A, I hope you can see in the, get my pointer. Forgetting. Laser pointer. So I hope you can see the A is in the corner in front of you. So just apply your mind a little bit. Okay, this is an easy example because let's say the face ABED, okay, is, let us say, perpendicular to in fact both the orthographic planes. Okay, projections of lines and planes. Mentally map it, and I'm going to show you now how it's going to look like in your front view and top view. Okay, straightforward. Okay, all the 4 point A and B both. Okay, the line, because the line is perpendicular or parallel to one of the orthographic planes, it collapses into a point on the vertical plane, and the point is same. A dash B dash is the same point, but C is a unique point. Okay, C is a unique corner point, so you only see dash only one there, and similarly C in the top view you only see 1 point. But again, A and D are along a line, and line is perpendicular to the horizontal plane. So both A and D collapse into a single point, which is denoted by A and D in the same place. Right? And once you know the position of AD and your BE, okay, in the top view, and C of course is unique point, you join them and you're getting the projection of the entire solid. Projection of the entire solid, right? So this triangle which you see in the top view represents both the top face as well as bottom face of this object. And what you see as A dash, C dash, F dash, and D dash is the projection of, maybe you can say, the face B, C, F, and E, but that contains also the two other faces. The two other faces, which is A, B, E, D and A, C, F, D, are also kind of within the projection of the face B, C, F, and E. Okay, and later on you will see that if the line AD, if it was not along B and D, then it will come up as a separate line in the middle of, in between this, in the front view. But because AD is along the B, it is not seen as a separate line. It is coinciding with the B and D line. I'm taking a little bit more time so that you are mentally very clear. And as it gets complex, you have to stay with me and understand how it is happening. Now we will look at the axis is perpendicular to VP, but the faces are no longer are parallel to any of these things, right? So if you look at only the bottom face, let us say, is let's say parallel. Okay. So if you see the actual object, which is A, B, O, and D. So O is the vertex of the object, let us say. Okay. But A, B, where is? Do we not need C here? This is C, right, Raymond? It is missing here. I'm assuming this should be C because A is A dash, D is D dash, B is B dash, and so this must be C here. Okay, so just think about it. And O is your let's say top of the vertex. Let us say it's a pyramid. O is a vertex, and what we're talking about is the axis of the pyramid. It's sphere pyramid. All the four faces being, let's say, similar. Okay. This axis is perpendicular to the front view in this case. Are you with me so far? Prabhat, am I audible, visible?
Yes, sir. Yes, sir.
Okay, okay, thank you. Okay, so now look at the definition of the problem itself. It's a square pyramid. Its base is 40 millimeters side. Okay, 40 millimeters side. Axis is 65 millimeter, which is O, and the perpendicular meeting the base is 65 millimeter long. Okay, has its base in the vertical plane, and one edge of the base is inclined at 30 degrees to horizontal plane, and the corner contained by that edge is on horizontal plane. Okay, what is saying? One edge of the base. So this base is not exactly this ABC. Easier option would be that if one of the edges of the base is also, let's say, parallel or perpendicular to the reference planes. No, we are making it slightly complicated. This square pyramid, it is also tilted, or let us say, you can say, yeah, tilted is a good word, with respect to the, or turned, rotated with respect to the vertical plane. How much rotated? 30 degrees here. Okay. So let's say that the point D happens to be on the XY line. In fact, you can make the XY line passing through, let us say, the point D. So that's taken care of that. So D is marked, which is D dash, same as on the intersection of D with either of the planes, which is XY plane. And now you know how to mark. You can draw this DC line because that is given to you, which is 30 degrees. Now you know the length of D dash, C dash, C dash, B dash, B dash, A dash, A dash, D dash. Because once you know this, four perpendicular lines, which is 40 millimeter side, that you are able to draw. Right? And how will you draw your, and then you know the intersection of these four, that is your point O dash, that is a projection of O on the vertical plane. From O, we're going to draw a projected line, and you keep drawing that until what? How do you make the 65 millimeters? How do you get that? Is O dash 65 millimeters? How will you get the point O is what I'm asking you. Answers.
We will measure 65 millimeters from O dash.
Okay. Everyone agrees to that? Is it 65 from O dash or from XY plane? I'm just messing with you. Is it 65 from O dash or 65 from, let us say, the XY line?
It's from the XY line.
Okay, we have two answers now. Should we take votes? Think carefully. Remember, the base is on the vertical plane, which means base actually collapses. If you had seen from one edge of if you see in the profile view, let us say, okay, or even in the top view, okay, the base. This is your front. This is your front view, right? This what you're seeing is a front view. This is your top view. In the top view, what is ABCD? In the top view, ABCD is collapses to a line. Yes or no? Right? In the top view, because you're seeing from the top, all these points ABCD collapse into a line. Right? This whole plane collapses to a line because the plane is parallel to the vertical plane. In fact, on the vertical plane itself. So is right here, right? So A, projection of A, right? This is your, D dash is, doesn't matter, it's D, right? This is your B, right? This is your C. So all this ABCD is nothing but the base seen in the top view. And if this is the base and this is the top view, all you're talking about is the height of the point O from the base, then this is what is your 65 millimeters. Clear? Everyone is clear? Okay. So now we will also projection of a solid on a plane to which its axis is perpendicular will show the true size and shape of the base. So what you're seeing here, A dash, B dash, C dash, D dash, is actually the true shape of the base of the pyramid. Okay, that's obvious. Now, something very similar, not just we are reversing the whole thing. Now we are saying that a triangular prism, okay, whose base is 40 millimeter side, height is 65 millimeter, is resting on horizontal plane. On one of its, it's a triangular prism, right? What is triangular prism? So it is two sides are triangles, other three sides are rectangles, correct? Normal prism, right? Two triangular faces and all other three faces connecting the triangles are rectangles. One of the rectangular faces of the prism is resting on the horizontal plane. Now, how will you project it? I'll give you a couple of minutes to yourself think about it. And this was a case I was telling you earlier. The base, the projection of the base, in which view, think about it, in which view, top view. The projection of the base in the top view, okay, will now contain the projection of the two side faces also. In fact, the edge, the top edge of the prism, let's say prism is like that, right? The top edge will now also be visible. In fact, the prism is like this, right? So not only seeing the edges of the base, you're also seeing the line on which the inclined faces meet, and that line also is visible in the top view, which is now seen as this line. Okay, so straightforward, not a difficult one. So because I want to go through ahead, this is something you can figure out in case you still have a little bit of doubt. But now I'll just show you this, and I'm not going to discuss this in too much detail because we have very little time now. But I'll leave the PPTs with you, and of course the book is also with you. But just think, although there are a lot of lines here, when you actually follow the book in your mind, the way to read the book is to go through the sequence of the lines. Okay, that's why I was trying to get my TAs to do animation of this, but we are running out of time ourselves. But when you read the book and read the exercise, or even these steps here, you follow mentally, think about only that line which is being talked about at that point of time. Otherwise, your mind will get cluttered. So what is the problem here? It is not pentagonal prism. Basically the two sides of the prism are pentagons. Okay, maybe pentagons, maybe all rectangles are maybe same. I think base 25 millimeter, axis 50 millimeter. So it's all rectangles have the same let's say length and breadth, right? So the length of the prism is 50 millimeter, and each side of that prism face, okay, the pentagon face is 25 millimeters. Essentially, it is 1:2 ratio rectangle here. And again, fortunately, the base is resting on the horizontal plane. So it's nothing but the previous case, what I showed you just now. Instead of triangular prism, instead of a triangle here, we're talking about a pentagon here. So it's not very difficult. Just you have to map it from that. And now what will happen is something interesting here. And I'll just make that point and leave it to here. I mentioned earlier that in case of this prism, the base, the projection of the base of the prism contained the projection of the two side faces also. But now it is no longer true because the side faces are now more than the base. Correct? So what we are now seeing is a projection of one side face, second side face, and the base. Three things. The projection of that will contain the projection of the top two faces also. So if you see from the top view here, just look at the last picture, the two here. Okay, you look at the A, C. It doesn't matter. This whole thing. So the outermost rectangle here is nothing but the total projection of the object, which includes three projections. Okay. Of course, we are seeing from the top view. So actually, we are seeing projection of the top two faces. So what it contains is this line in the middle is nothing but the top line of this pentagonal prism, right? And what you're seeing as the two rectangles on two sides. Ignore the dashed lines for the moment. Okay, the two rectangles on two sides of the middle line are projections of the top two faces. And the dashed line which you see, okay, they represent the outermost, the dashed line and the outermost line represents the projection of this face. And similarly, on the other side, this face, and this is represented by the distance between the two dashed lines, because this bottom face is not visible from the top. It is a hidden line. So what you're seeing here is the hidden projection of your base. Okay, so once you figure out that, construction is straightforward for you because you already know the construction of now even the planes, right? But again, this is a simple case because the base is parallel to the horizontal plane. And there are two methods which you can look at it. And this is also axis is inclined to horizontal plane and parallel to vertical plane. Basically, what you're doing is it is, and you can start looking at, for example, now, if you wish, auxiliary planes. Okay, I will not talk about it because too short a time to discuss, and you will have your own doubts. But I'll take it as a home exercise for you to figure it out and then apply that in your next class. And the final one is we're taking a simpler shape now, a square prism. I think, but rectangle actually. Rectangular block. All the faces are rectangles, no triangles, no pentagons. But now we are saying that it is no longer any face or no face of this rectangular block is parallel or perpendicular to any of the reference planes. So simpler shape, but inclined to both the planes. And again, once you know how to project each of the planes and project the planes which is visible, and then hidden lines you map it a little later. You're done with this kind of. So I'll stop here, and you have only other thing is a projection of spheres, but that is very straightforward because sphere is a great thing. No matter which direction you see, a sphere is always a circle. Right? That's a good thing about it. So all you need to know is where is the center of the circle. As long as you project that in your orthographic plane and you know the diameter or radius of the circle anyway, you can project a sphere in any place. But this question is now making it a little more interesting for you by saying it is not one sphere only, it is 3 spheres, and tell me how they will look like in a projection, reference projection. Okay, so we'll leave it with you, and summary nothing but what I said to summarize that. But please, as I mentioned to you earlier, do not only rely on our classes and slides. Please go back to the book, because I think it's an additional understanding for you. And I repeat that this whole course, this whole lab is all about getting you to do two things. And I repeat that. One is that you start visualizing things in 3D space. Thanks to CAD and graphics and computers and all that, you will see when we go to the last class that you do not really have to do that, because computers take care of it. But it's like saying that, okay, I don't need to calculate or multiply because I have a calculator or a computer for doing that. No, this is like a life skill for an engineer. Okay, so visualizing these shapes in 3-dimensional space on projection planes, and the 9th class you will see the reverse of the whole thing. Given a projection of a 3D object, construct how it will look like in 3D space, and that's going to be challenging for you at the last but one class. Okay, so with this, let me close this class, and let me look forward to the next lab class, where you look at projection of planes. Solids is not very difficult because it is extension of that. And after that, good luck for your campus return. I don't know how you're going to come back, by plane or a train or maybe a ship, I don't know. And good luck to campus return. I'm sure you're excited. I'm sure the parents are excited. But be safe. I think Corona is still not out. Do take all precautions, and wish you safe return, comfortable return. And then we'll see how the next classes go. Most probably next 2-3 classes we'll still do online mode, but we would really like to do at least 1 or 2 classes in physical mode as well. But we will see when it get to that. Okay, and I told you about midsem exam. We will send the notice on Moodle, and you can mention that to others who missed today's class. Okay, with this, let me close today's class. Any quick question?